expectorant. It's a class of mucokinetic drugs used for clearance of the airways. So it's your lung, your bronchi, your windpipe, so that's an ionizer. And it's also used to treat thyrotoxicosis. It's a disease that you will have overreactive thyroid that produce a lot of thyroid hormone, and it's also for blocking the radioiodine uptake of deuteriodine. And it's also used for povidone iodine. It's a chemical complex of polyvinyl pyrrolidine, which contain 9% to 12% iodine. It's mainly used for antiseptic purpose for cleaning wound, health, and body. Absorb X-ray due to electron density and atomic number acting as a radio contrast agent. So acidity. Some general facts about acidity: has the highest boiling point, melting point, and then lowest electron activity 2.2. Characteristics about acidity: it's a result. It's not a natural exist. It's a result of radioactive decay bombarding bismuth 209 with alpha particle. You get acidity 210. That's one of the longest. Has the longest half-life, about 8.1 hours. So and the element acidity has never been viewed due to self-generating heat from reacting because it's constantly doing the decay mode. And some of the compound are acid, bromide, acid, chlorine. And for a little bit application for acidine 211, it is used as nuclear medicine for targeted alpha particle radiotherapy, and it also has a similar manner to iodine targeted to thyroid cancer therapy. But acidine 211 is more preferable. It's much more preferable because it's low energy beta particle. It has low energy beta particle than iodine. It travels 70 micrometer to the surrounding tissue compared to iodine 2100, and then it has short half-life and limited penetrating power, so it's important. And then we have
purple. This is more fun than actually being did it live. All these reactions stink. So. Really? I think they make some of these Chinese firecrackers with this, right? Oh, this is the best one I've been using.
Why is it always Mexican guitar? The end.
not really used in the bulletproof vest, but it's used as the outer coating, like, you know how they have like the actual vest and they have the coating? Yeah. So it's like they make airbags with it, like, it's like that kind of material. Plastic nylon. So, but it's not.
You have only the single-sided one too.
Yeah, it's really stressful. Oh my God. So much work. No, it was so much work at the time. I got that in
Hello, everyone. Thank you. So I'm Lauren Miller, and this is Rebecca Korf, and we are going to be talking about the noble gases.
Okay, so just a little bit of introduction about the noble gases. They are inert, so that's why they're noble, because they don't mix with the other common elements, they're kind of stew, we like to say. And the reason that they don't mix with the other elements is that they have that full valence shell of electrons. So helium has 2, and then all the others have that 8 in their shell. So they're happy just fine being like they are. So they aren't too apt to mix with other elements. And that's why they're slow to form compounds. Actually, until the 1960s, we didn't think that they could form bonds with elements at all. In the 1940s, scientists were able to prepare clathrates, which are basically like little cages. So they have holes in the lattice structure that could trap the noble gases, and that's the only way we were even able to get them to form compounds. Now, in 1962, we were able to get xenon to form a compound with fluorine, and I'm going to talk about that a little bit later when we talk about xenon and fluorine. And then just to show you a little bit more about noble gases, we have this lovely video. We'd like to continue.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all.
This is an old video.
As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Sorry, that's my favorite part.
Okay, so just a little bit of the history of the noble gases. We didn't actually know that they existed until almost 1900. So we had a couple puzzles, though, that led us to think that there might be these noble gases. So the first was in 1766. There was this guy named Cavendish. He was trying to show that the air that we breathe is not all the same element. So he would separate out the oxygen, then he'd separate out the nitrogen, and he'd separate out the carbon dioxide. And there was always just like a little something left that he couldn't get to react with anything. It was like less than 1%, but it was still there, and he couldn't get it to react. So it was this puzzle. And that puzzle went unsolved like 130 years. And then in 1894, when they were just doing some experiments with nitrogen, they had figured out how to isolate it. And there were two different ways. They could separate it out from the air, or they could separate it from ammonia. And the one that was separated out from the air was slightly heavier than the one separated out from ammonia. And if these are the same compound, or if this is the same element, why do they have different densities from different sources? These scientists were really confused. And eventually what happened was a year later, in 1895, William Ramsay was able to show that the reason why that nitrogen gas we got from the air was heavier is because it actually was a mix of mostly nitrogen and then just a teensy little bit of argon. And that argon was what was making the density different, and that's also what was left in the air after Cavendish separated it. So he said that this was a new element. Now by this time, we already had our periodic table pretty much figured out. There were spots that were open, but either by its molecular weight or by just the way it acted, it didn't seem to fit in there. And at this point, Mendeleev, the guy who made the periodic table, he was still alive. And he saw argon as a threat. He said, because if this doesn't fit in the periodic table, then it meant that his periodic table was wrong, and he did not want to be wrong. So what he said was that it wasn't a new element. It was actually just N3. And they were bonded so close together, it was almost like a sphere. And he tried to convince everybody that that's what happened. Some people believed him. Most people were able to say, no, it seems like it doesn't fit. And then they found helium and argon and neon, and it became obvious that there was a new group. Now this new group, when they added it to the table, actually made a lot more sense. It fits in with the periodic table very well. However, Mendeleev still wasn't super happy about it. The reason that he didn't win a Nobel Prize in 1906, he was nominated for it, but they decided that because of his behavior with this new atom, they didn't get it. So, and then he died a year later.
It was an emotional time for the guy. Okay, so here is just all of our noble gases, and so you can see all of the periodic trends. Obviously, they get heavier as you go down, and ionization energy actually is less as you go down, but they're still all really high. Just to compare it to, sodium has an ionization energy of about 500. So when you're going up to 2,000, it says it doesn't want to do much, really. They all have obviously super low boiling points and melting points because they don't really like being anything other than a gas. And technically, they are all in the air right now, just in very small amounts, some of them.
So every breath you breathe is about 1% argon, but very small amounts of the other ones. So now before we talk about helium, we get to do a cool demonstration with it. Yeah. So I got this balloon from Safeway. It's helium gas. You can tell that it's lighter than air. And we're going to show what happens when we light it on fire, or light it with a match. So, what's the best way to do this? So we're just going to, I think that you guys are safe. We think, if all goes according to plan. So Lauren's just going to light the match, and we'll see what happens. Okay, everybody ready? Steel yourself.
Am I literally just lighting this balloon on fire?
Nothing happens. So,
Nothing happens.
But, yeah, nothing happens. That's because helium is a noble gas, and it doesn't do anything.
Including burn.
So, I was looking for demonstrations that we could do with the noble gases, and all the cool ones occur only at about 1 degree Kelvin.
Or they cost like $700 by making the little actual neon signs and showing electricity, and I wasn't willing to do that.
So you get to see exactly why helium doesn't react with things. So just a teensy bit of history really quickly. It was actually discovered on the sun before it was discovered on Earth. Because in 1868, an English guy named Lockyer was looking at the sun with his little spectroscopy thing, and there were these yellow lines that weren't matching any other known element. And he named this, he thought that there was a new compound. He named it helium after the Greek helios for the sun. This actually became a little bit of a joke, kind of like a unicorn. So if you would like theorize this thing and you were a scientist working in a lab and other people thought you were just crazy, they'd tell you, oh, that's just helium. But he was vindicated in 1895 when it was isolated by Sir William Ramsay. It's not too common in the Earth, very small amounts in the Earth's crust, a little bit in our atmosphere, but it's actually the second most common element in the universe. Hydrogen is about 90% of our universe. Helium is the other 10%, and the rest is what one of my books called a cosmic rounding error. So it's very, very small amounts. So helium is pretty prevalent once you get outside of the Earth. There are no known compounds that we have been able to confirm their existence. Now, in 2002, there was this experiment done where they think they might have produced this compound, hydrogen, helium, and fluorine, but it has a lifetime of about 120 picoseconds, which is too fast for them to be able to tell if it even existed, let alone characterize it. So it theoretically could have existed, we just can't confirm it. Okay, so I was talking about the cool things we could do at low temperatures. It's a super fluid once you get to 1.7 degrees Kelvin. That means there's no viscosity and no friction. So if you put it in a glass and suspend that glass, it'll actually crawl up the sides of the glass and around and drip down. It's used primarily for weather and party balloons like we just showed. Dirigibles, which are those airships like the Hindenburg. It's a lot safer than hydrogen. So if we had done that demonstration with a hydrogen balloon,
We all would have died.
yeah, we all would have maybe lost a little bit of our hearing. And it's a lot safer, and that's why we use it for that. So another cool demonstration we could have done is to talk in that really high helium voice. That's actually really, really bad for you. I don't know if you've heard about that, but people have died doing that, so we're not going to do that. But basically, the sound that we produce in our voice box is made by vibrations, and the faster the air moves, the higher our voice. Helium is a lot lighter than the air that we breathe, and than most of the air that we breathe, so it just comes out a lot faster, which means that it goes higher. It's produced by radioactive decay, mostly from uranium. That's how they were first able to isolate it, and it's harvested right now from natural gas. The United States has a monopoly on it right now, mostly because it's the only place where it's produced. However, we have this price fixing scheme where it's really, really cheap, and so people aren't being necessarily conservative with it, and we think that we're going to run out of it really soon. It's not good because it's lighter than air, so it just floats out of our atmosphere. So pretty soon there will be no more balloons, or at least no more helium.
Okay, so now we have neon. I can talk. It's fine. So this was also discovered by Sir William Ramsay and Morris Travers in 1898. It was from the Greek word neos, meaning new, and they discovered it from using liquefied air, which is literally what it sounds like. They took air, they made it a liquid, and then they recorded things as they boiled off. So after we got what we already knew was in there, it was what we had left over. And from this process, we were able to get neon, xenon, and argon. So neon was one of the three. It is technically the fourth most abundant element in the universe, although it's basically minute amounts in our atmosphere for the exact same reason of helium, where it just keeps on going past the atmosphere and keeps on going somewhere else. I don't know. It has no known compounds, even as now, and when it's sealed with a tube and applied with electricity, it glows, which is where we get our neon signs, which were discovered by George Plot in 1910 in Paris. He patented the idea in 1915, and then in 1923, he brought neon signs over to America, and the first two signs he ever sold were to Picard car dealership in LA. For, I believe it was $24,000. That is equivalent to about $320,000 now for 2 neon signs. And I won't make you guys think this because that'd be awkward, but it's to the tune of Rudolph the Red-Nosed Reindeer, and this made me smile. So, neon, the noble gas, had a very full octet. He thought about reacting, but he hasn't done it yet. All of the other gases ionize so readily, but not that little old neon. He was stable as could be. Then when Drury dark and dreary eve, George Claude came to say, "Neon with your shell so bright, won't you light my sign tonight?" Then all the gases loved him as they shouted out with glee, "Neon, the noble gas, you'll be big in chemistry." Other uses, other than the advertising signs, are high voltage indicators, lightning arresters, wave meter tubes, and television tubes. And I found this t-shirt, which I thought was funny, because apparently someone takes neon very seriously as an element. So, yeah.
So argon was discovered 1895 along with neon from that liquefied gas. Argon means lazy. They did it because it's not willing to work with any of the other elements. It's present in very small amounts in the Earth's crust. It's actually the most prevalent in the air that we breathe. And there were no known compounds until 2000 when they were able to make this one from hydrogen, argon, and fluorine. It's only stable at or below 7.5 Kelvin. So very, very, very cold. We use it mostly to provide an inert environment for chemical reactions. So ones where we could be concerned about the oxygen or the nitrogen in our air joining in because it doesn't react with things very easily. It also fills incandescent bulbs, which are falling out of favor, but you have one of those old antique ones. Those have argon in it. It's produced by radioactive decay, and again, it's harvested from liquefied air. So,
Krypton, once again, discovered by Sir William Ramsay and Morris Travers. It was technically discovered about 3 weeks before neon, though. It comes from the Greek word for kryptos, meaning hidden. There's only a few compounds we know of. There's krypton difluoride, which actually wasn't discovered until 1963. And it's only about 1 part per million in the atmosphere. It's kind of negligible. Uses, we have it for high-speed photographic flashes. It makes very, very, very fast flashes. It's also in fluorescent bulbs. It's argon and krypton mixed together. Luminous signs, because it also turns a pretty color when it's hit with electricity. And sometimes in double glazed windows, krypton is what is in between those because it has a higher molar mass than air, so it doesn't conduct heat as well. So it acts as a better insulator. But overall, there's not a very many uses because it is so hard to extract from the air, it makes it really expensive.
okay, so xenon was discovered a little bit later than the rest in 1898. That's just because they still had to figure out how to boil more and why that off. Xenon means stranger in Greek, so again, it was difficult to find. It's present in very, very small amounts in the Earth's crust and in our atmosphere. But what makes it really special to us is that it actually makes compounds. Yay! So in 1962, there was this guy named Bartlett, and he was able to mix xenon gas with platinum fluorine gas, PTF6. That's actually a metal compound that's its gas. It's very, very volatile. And in mixing them together, he was able to produce xenon fluoride, xenon F2. And this was voted by the American Chemical Society as one of the top 10 most important chemical experiments done in the 20th century because it showed that these noble gases can make compounds. And we use it, we've drawn Lewis structures of it quite a bit. So we use it as a general anesthetic actually, and also in lamps. The lamps that light the Niagara Falls are made out of xenon. It's most useful, however, in scientific study just because it's so rare and so expensive. So we use it in studying how the Sepper theory would predict things acting, and then we can actually test it with xenon with this extra extended octet. It's produced by radioactive decay, and we actually think that we're missing some in the Earth because there's a lot more of it in meteorites than there is on the Earth's crust. So we think that it might be existing somewhere as a xenon oxide. And our book says that we don't know what's going on Mars. They say the situation on Mars awaits further exploration, possibly by you or another reader of this text. So you, as readers of this text, can go explore Mars and figure out xenon. As Lauren mentioned, it's harvested from air. It's really expensive. In order to fill a balloon that size, it's about $1,500. So that's why we didn't have a xenon balloon.
I got through $1,500 on the roof. Okay, so lastly we have radon, which was discovered in 1900 by Friedrich Ernst Dorn. He was studying how radium decayed and discovered, hey, something else is made, just like a lot of other stuff happens. It was actually originally called niton, which means shining in Latin, but in 1923 they changed it over to radon. I didn't really find out why. They just decided that's what they wanted to do. Radon 222 has a half-life of about 3.8 days. That's the most stable isotope compared to a bunch of the other half-lives we've seen. That's technically a really long time. So it can be used sometimes for treating cancer in very small amounts. The only confirmed compound that we have is radon fluoride, which isn't that commonly used. But it can happen, and that's a really big deal. And there are all of our references. Questions?
Okay, you said that was discovered in 1898, but then for the other, you said it was discovered at the same time as argon and krypton.
Within a few weeks.
Okay, and then, but you said 1895 for krypton.
So there's a little bit of a disconnect between when it was actually like theorized discovered and when it was published. So I think that's where those.
Okay.
Yeah. So and like again, we didn't know that it existed. So there's all this flurry of like scientific, we're discovering new elements because most of them had already been discovered. So these people like they thought they found them, and then at least said no, you haven't found them, and then they said well, we found them. So that's why the dates are a little bit.
Okay.
Well, thanks, guys.
Radon is really interesting in Spokane. There's a large amount of radon, so since it's radioactive, it's one of the things that if you own a basement in Spokane, you are advised to test for radon levels because the radioactivity around here is higher than going and visiting Hanford. And it's from natural radiation, mostly from radon and from other radioactive rocks. But you can build up those gases in your home. If you do discover that your basement has radon, they put in air exchange, basically tubes and fans, so that you can exchange out the air so that it doesn't build up. And the radon, being heavy, settles and then slowly filters up. So most of the time you're testing in the basement.
What else ocean has, but why, how's it naturally produced?
I think it's just by radioactive decay. So there are some elements that are common just in the crust around Spokane that they'll kind of decay off and release that radon, and then it floats up very, very slowly.
That makes sense.
I think it's related to like proximity to volcanic activity a little bit or something like that. I haven't looked into geology.
Yeah, so from rocks, from things, so radon gets more press around here than it does in some places. Take a minute to write down your questions. Probably promises will get it. Okay. I don't want to talk about diodes in 3 minutes. So, we're done.
Thanks.